Okay, hi guys, I'm John Hurley from Netronome, and we're going to talk here about offloading the open vSwitch datapath to a SmartNIC, and really executing all the match fields and the actions of the datapath on that SmartNIC. And in doing so, I want to focus here on one of the problems that we tried to put forward a solution to this year, and that is what happens when Linux lag devices start becoming involved in this. So by way of introduction, this is the kind of standard TC-FLAR based model to offload the data path of OVS to a hardware device. This is kind of the approach you want to take if you want to do things in line with the upstream Linux kernel. So the idea here is that we don't technically replace the OVS kernel data path, we kind of supplement it with a TC-FLAR data path. So TC is like the traffic control subsystem within Linux, and it works on the idea that you apply what they term a QDisk to a given netdev or a port. To this QDisk, you can then apply, say, traffic shaping algorithms, congestion control algorithms, but you can also apply filters. And the filters that we apply here are called TC-FLAR. We'll have an example of, I think it's just in the screen here, of an OVS kernel rule and a TC-FLAR rule. It's effectively the same rule. If you look at the syntax, we'll not go into it, but really the only difference here is that the OVS rule, or the OVS kernel rule, actually matches on a port. The TC-FLAR rule is kind of applied to a port, but effectively we get the same outcome. So why do we want this TC-FLAR data path in here? What is the purpose of that? Why don't we just use the kernel data path? Simply because within the FLAR subsystem and within the TC-FLAR section here, there are offload hooks that allow us to hook in our own netdevs and to receive information about any flows that are being offloaded. So if, for example, we put in one of our SmartNICs and we load our Linux driver, which is in the upstream kernel called NFP, this will generate a series of netdevs. These netdevs we've named here, say NFP P0 or P1, will represent the actual physical ports on the card itself. We may have other ports then, for example, I have V0.0 here, which may represent a VF that we can use things like SRIOV to get direct linkage from the SmartNIC to one of the VMs running on the system. So when we generate these netdevs here, we actually register within TC to request any offload information. If we add a new QDisk to one of these netdevs, then our driver hears about that. Similarly, if any FLAR filters are applied to that QDisk, our driver hears about them. It can simply package up the rule into a format that the card understands and write that information to the SmartNIC. So this is kind of our motivation for doing this. I'll not dwell too long. It's not really the point of the talk. But these are some performance figures we get. I think the test here is some VXLAN traffic coming into the NIC, matching rules, being directed to a VM, bounce back to the card and back to the network. And I think the setup here compares it against OVS DBDK running with 8 cores. So the simple takeaway here, if our Netronome graph is in the blue lines, we are significantly improving the performance figures we get here. So yeah, our main goal here is the performance increase we see, but also when we consider that because we were doing this, most of the network data processing on the card, we are freeing up the CPU cores here. So lag devices, quite simply a way of grouping together a series of ports to kind of act as a single port. 2 real reasons to do this. Firstly, you may want to try and increase the bandwidth over a given link, so we actually load balance our traffic across the given ports, the given grouped together lag ports, and we thereby kind of improve the bandwidth efficiency across the link. Secondly, we may want a kind of active backup scenario whereby only one of our direct connections is up at a given time. The reason being, if that then dies or if we get some sort of issue with that, we simply flick over to another link and we still maintain connectivity. Open vSwitch itself handles this in terms of Open vSwitch bonds. From an offloading perspective, it's actually not a hard thing for us because the datapath rules generated from these OVS bonds, you can't really tell that they were generated from bonds. So effectively, to offload here, we simply want to take these datapath rules, package them up, and write them to our card. There are some issues with using OVS bonds in certain circumstances that have been reported by some of the OpenStack guys, where if you use a combination of OVS kernel, OVS bonds, LACP, and you have high throughput, there may be some link flapping reported. So some deployments of OpenStack choose to use Linux lag devices here. So Linux lag devices primarily consist of the Linux bond and the Linux team driver. I will probably use the terms now interchangeably, so if you hear me say bond or team, I'm talking about a lag device. But the point is, if we take one of these Linux lag devices and we add this to an Open vSwitch bridge, then how can we still offload the rules that are applied here if the underlying ports, the lower level ports of this bond, are ports that we're interested in, ports that we have actually are looking to try and offload rules to? So there's two scenarios here. Firstly is kind of the easier scenario for us. It is, I've called it egress offload. Effectively, we get a TC rule, as the example shows here, which maybe matches on a port that we are interested in, and does some match, but egresses to a Linux bond, for example. So to support this rule, we don't really need any information or interaction with TC or Open vSwitch. Effectively, at the kernel layer, our driver registers for net device notifications, namely the change lower state and the change upper notifications. And these are triggered by the bond driver and by the team driver when, say, a new upper layer master bond device is created, when lower level devices are added to a bond or a team device, and when ports are put up and put down by the actual bond to create this active backup setup. So from our driver perspective, we receive all this information, we track this information, and we make simple calls like, here's a new bond, are the ports, the lower level ports, are we interested in these? Can we offload them? Are they maybe physical ports on our card? If so, we package these together, we assign them a group ID, and we write this to our SmartNIC. If we see then a TC floor rule like the above that is egressing to, in this example, bond 0, we do a lookup, we find that we have a group ID associated with this bond, and we offload the group ID as an action to the given rule. When a packet arrives into the card itself will do a hash of the packet and use this hash value to select a given port from the group. And we effectively achieve the load balancing outcome that we want here. We also do our active backup in this same manner, but we simply only offload or only assign one port to a given group. So we kind of get that for free in a way. Ingress offload is more difficult and therefore probably more interesting. So I term ingress offload when we actually want to apply rules to a given bond that may have offloadable underlying ports. So we have an example here where packets are maybe coming in a given bond and doing some action and outputting somewhere. So the bond and the team driver within Linux aren't going to go and register for hardware offloads. This isn't something, there's no need for them to do that, and it's not something they do. So we have no direct link from a rule being applied to this kind of upper layer device and the callbacks that our lower layer devices have registered for. So we want to know, is there some way we can kind of bridge this gap and kind of hook this all together? So rather than going away and trying to design something new and come up with our own ideas here, we want to see if there are any features already available in Linux and possibly in TC that we may be able to make use of here. So the idea of TC shared blocks was upstream to the kernel and is available in 4.16. So if we consider a QDisk and a series of, say, floor rules applied to that QDisk, well, we consider all of these to be a block. So a shared block is effectively this set of rules shared between multiple QDisks or, and in turn, multiple ports. This wasn't introduced with bonding or lag devices in mind. This was, the actual use case for this, I think, was to better improve offload to TCAMs, whereby if you have multiple ports and we want to apply the same, say, ACL rules to all these ports, well then it seems a bit stupid to try and offload these rules for each port and write multiple copies of the rule to the TCAM, taking up extra unnecessary space. So they introduced this idea of grouping these together in a shared block and offloading one copy of the rule. Now, because this is happening at the TC level, TC then takes care of a lot of things for us here. For example, if we apply a new filter, we apply it to the block rather than to an individual QDisk. This in turn is distributed to all the QDisks that are involved in this block. And in the opposite direction, if a packet matches a filter rule on a given QDisk that is in a block, well then it updates the stats not only for that filter on the QDisk, but for that filter in all occurrences on the block. So then with this, we effectively want to know if we can use this TC shared block infrastructure to kind of have a representation of a lag device that we may be able to use here for offloading. So effectively, we have the kind of hierarchy of, say, a bond on the left here, where we have the upper device and the lower device, and then a block which doesn't really have a new netdev created for a block, etc., where everything kind of lives in the same level. But if we take the upper device and we add it to the same block as the lower devices, we effectively kill off this hierarchy here, but can it still work? And because the block idea only exists in TC world, then we think that yes, it can work. So we aren't actually affecting the functionality of the bonding device anywhere else within the kernel. So a few problems with this when we started looking at it, and I suppose the main issue here is that for the original use case of doing like the TCAM offload, there is kind of an all or nothing approach. So we kind of decide at the start that these ports are going to be grouped together, and we're going to offload rules to all these ports, and then when we're done, we remove all the rules and we kind of separate the ports again. There's no kind of, in fact, it's blocked if you use kernel 4.16 to 4.18. There's no kind of ad hoc approach to this, whereby if we have a block that has offloaded rules, we can't just add another QDisk stroke port to that block and associate this with the same rules. Similarly, if a block exists that has offloaded rules and we remove a device from that block, then the device that is removed, the QDisk, does not have its callback function triggered to remove the rules that exist. So you can get into a lot of, if you're doing hardware offload, you can get into a lot of synchronization issues here. Again, this is something that we want to try and achieve, to properly offload lags, where the idea of adding a device and removing a device can be done as frequently as you may choose to do, and we would like our rules to keep up with this without having to, say, modify our upper layer OVS bridge or something. So we released a patch set, which is in mainstream kernel 4.19, that introduces this idea of re-offload. Effectively, what this does is that if we have a TC shared block with multiple QDisks and offloaded rules, we add a new QDisk or a new port to this block, well then it triggers this re-offload function. So it takes all the rules that are already offloaded and it calls the hardware offload hook for the new QDisk. Similarly, if we pull something out of the bond, the same hook is triggered and the re-offload sends all the rules, but this time with delete messages. So we can keep our offloads, our offloaded rules, the rules that are actually on the card, in line with what is on the TC shared block representation. So now that this kind of shared block setup kind of imitates what a lag device is doing, how do we tie all this together? So we released another patch set for Open vSwitch, which went into 2.10. And yeah, effectively this updated the OVS TC API in the user space daemon to allow it to understand the concept of shared blocks. We track the kernel netdevs through the netdev Linux file, and we record any information on lag devices, and we associate that with the netdevs here. So if a lag device or upper device is, so say, a bond master is applied to an Open vSwitch bridge, instead of just adding a QDisk to this that may be used for TC offload, we apply a QDisk and a block ID, a unique block ID to this upper layer device. We then monitor the other net devices from the kernel, and if we see a lower level device, so that has a master device that is on the OVS bridge, then we associate this with the same QDisk and same block ID as its master. So even though these lower layer devices are not necessarily added to the OVS bridge, we still give them the same block ID of the device that is added to the OVS bridge. And yeah, effectively we get kind of at the top here, this red dashed box, which kind of shows what Open vSwitch knows about. We have OVS, and it knows it has a TC data path. It knows there's a device on this data path, and it will happily write TC floor rules to this device, and will happily pick stats off from this device. The kind of blue dashed line then shows what our driver knows about. It knows that it has these two devices here, these lower level devices, and it knows that these have registered for hardware offload hooks that it cares about. And anytime it receives a filter, say, passed here, it will package it up and write it to the SmartNIC. Similarly, it will extract some of the stats from anything that matches on our SmartNIC and update these lower level devices. And the thing that ties it all together is then this kind of green circle with a block ID. And this kind of links this pure TC land. It links together this kind of upper layer device with its lower layer devices that all comprise the bond. And yeah, effectively, this is how we get our top-level Open vSwitch bridge communicating with our SmartNIC through Linux lag devices with minimal changes, using what is already in the kernel, making minimal changes to some of the TC stuff, and minimal changes to the Open vSwitch TC API. And that is a summary of some of the work we've been doing this year.
Let's thank our speaker. And we have time for questions, so please come up to one of the mics.
Hi, I have a quick question. Does this work also if you have different physical NICs and then have multiple VFs into the virtual machine, so you load sharing across NICs rather than on a single NIC?
Yes, that can be done.
Okay.
So you mean kind of, we can encompass VFs into a Linux bond, yeah, sure, and then offload this functionality. Yeah, that's okay. Something we can do.
Okay, yeah, but on two physical NICs, right? That's what I'm trying to see. So you have NIC redundancy, so you have two NICs, have a VF from both NICs into the virtual machine.
Okay. Yes, it would possibly be rejected at the minute because from our driver if it doesn't recognize the output being to the VFs don't exist on the same NIC if we're doing egress here.
But on egress, it can take always the one VF, right? I'm just trying to see for a redundancy
yeah,
perspective.
the problem here is that the NIC itself does the hash and uses that to kind of select the output. So it could cause some issues here with fair kind of load balancing.
Okay.
From an ingress perspective, it should be fine because we don't really care where the data comes in as long as the stats are all updated, even if only one of the lower level devices exists on the one card. The others may be anywhere.
Okay, thanks.
Hi. On your previous slide, could you describe what combines the stats together from the two bottom devices? Because if TC is only seeing the TC block, how can each lower device contribute its stats?
So this is kind of handled within the TC shared block code. So for example, if a packet comes in, and let's use the example here, matches on the SmartNIC where I have lower device 1 there. On our SmartNIC, it will only update the stats for that particular rule. When that's passed up to the QDisk in the TC data path here, because it has updated the stats for that rule, it updates them within the entire block. So effectively, the stats on the upper device will never be kind of updated in that a packet will never hit the upper device here. But because we're updating the lower devices, it automatically updates the upper device, and that's all that OVS sees.
Any more questions? All right, let's thank our speaker again.
Thank you.